Okay, we're going to talk about some more types of reactions, of precipitation reactions. If we take aqueous lead-2 nitrate, there's the formula for that, and add it to aqueous sodium iodide, both of these are soluble in water, and they're actually colorless, clear solutions. If you look at a beaker of each of them, they look like water. You can't tell the difference by looking at them. So when we pour these together, though, we get a yellow solid that forms. It looks like magic. It looks like you took 2 glasses of water and poured them together, and then you can get this yellow stuff. This is really fun. The yellow is the lead iodide, lead-2 iodide. And then we also have sodium nitrate that is present as well. So this solid, it's an insoluble product. It won't dissolve in the water, and that's called a precipitate. And any reaction that forms a precipitate is called a precipitation reaction because it forms a precipitate. So let's look at what's really going on here. Lead nitrate is an ionic compound. Is it a strong electrolyte? Yes. Ionic compounds that are soluble in water are strong electrolytes. They dissociate completely. You don't have individual formula units floating around. You have ions. So what this is really doing in solution is we've got Pb2 plus ions, and we've got NO3 minus ions. It separates. Is sodium iodide a strong electrolyte? Yeah. It's an ionic compound. It's soluble in water. And so this separates into sodium ions and iodide ions. So we mix these things together. We now have a beaker that's got lead-2 ions, nitrate ions, sodium ions, and iodide ions. And they're all mixing around together. So this is where I'm going to tell you another one of my crazy analogies. I think of this as people going to a party. And I've told you before that I think of metals as being masculine and non-metals as being non-masculine or feminine. So these negative ions are the girls, and these metal cations are the guys. So lead and nitrate are going to go to the party together. The party's in a big beaker. And sodium and iodide are going to go to the party. And what do people do at parties? They party, right? They mingle, right? When you go to a party with someone, do you stay attached to them through the whole party? Usually not. Because if you wanted to do that, you would have just stayed home, right? So you go to the party and you mingle around. So these ions are mingling around, and they meet each other. Sodium maybe hadn't met nitrate before. Lead-2 hadn't met iodide before. And so what happens is lead-2 plus ends up talking to iodide and realizes that she's really hot. And she thinks he's really cool. And they're like, where have you been all my life? And they're like just really attracted to each other. And so they quit mingling around the party, and they go off and find that couch on the back porch. And they do whatever people do back there, right? And nobody sees them anymore. They settle to the bottom of the beaker. They're insoluble. They're not going to mix anymore. What happens to sodium and nitrate? So sodium's like, I can't believe iodide just left me like that. And here's sodium, nitrate, and nitrate's kind of feeling a little left out too, and so they're going to talk to each other, but they just, I don't know, nice person and everything, but there's not that chemistry, right? So this symbol here, aqueous, means that the sodium ions and the nitrate ions are still floating around in the solution. They're still mingling like everybody else at the party. The solid says that lead and iodide formed an insoluble complex, an insoluble compound. And solids are heavy, and they settle to the bottom. If you wait, all that yellow stuff will settle to the bottom of the beaker. They're off on the back porch necking or whatever. Okay, so that's my analogy for this type of reaction. Here we have some pictures. So here we have the beaker containing sodium iodide solution, clear, colorless. Here we have the lead nitrate solution, also clear and colorless. And you mix them together, and just like magic, you get this bright yellow stuff forming. And you may think, well, that doesn't really look like a solid. That's all swirly. And we can tell it's a solid because it's opaque. It's not translucent. You can't see through it anymore. You can have yellow solutions. That's what my boys leave in the toilet when they forget to flush, right? It's a yellow solution. It's clear, but it's yellow. It's not colorless. But this is opaque. Sometimes we say it's milky, right? You can't see through it. And if you wait, all of that yellow stuff settles to the bottom. That's the lead 2 iodide. It's not soluble in water. We didn't have any of that yellow stuff over here because the iodide and the lead were separated. It's not until they had the opportunity to get together that they hooked up and became a precipitate. Any questions? There are lots of ionic compounds that are soluble in water. Over here, this solution was made by taking solid sodium iodide, which is pretty similar to sodium chloride, and dissolving it in water. You can go home and try this. Take a cup of water and a teaspoon of salt. Put the salt in there and stir it up. What happens? It dissolves. The salt seems to disappear, doesn't it? You can't see it anymore, but it's still there. If you taste the water, you can tell very clearly there's salt in it. It's just become a homogeneous mixture, a solution. Sodium iodide, sodium chloride, very soluble in water. Lead nitrate is also soluble in water, but not all ionic compounds are soluble in water. And when you mix two solutions of ionic compounds, you do not always get a precipitate. You only get a precipitate if one or both of the products of the reaction are insoluble. Just like every time people throw a party and lots of different people show up, you don't have this like match made in heaven occurring, right? Some parties, nothing really happens. And other parties, people hook up and they stay together for a long time. When we talk about solubility, it's actually can be measured quantitatively. It's defined as the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. And for our purposes at this point, we're just more concerned with, does it dissolve significantly or does it not dissolve significantly? Well, how can we predict if things are going to dissolve or not? The periodic table is not a whole lot of help in that. The factors that cause some ionic compounds to be insoluble and others to be soluble are very complicated, and you do not want me to explain them to you. And so the simplest thing is to memorize a set of guidelines, or some books call them a set of rules, solubility rules or guidelines for solubility. So here you go, something else to memorize. These rules are empirical, meaning they're derived from experiment. Many people have done many experiments. It's like, well, let's take calcium carbonate and put it in water and stir it. Does it dissolve? How much of it dissolved? And then they write it down and they make observations, and other people do similar things, and then we collect all this information together. So I've tried to present this information here in a way that's easy to memorize. Okay, these rules are also on the green card that I gave you, but I think they're a little harder to memorize in that form. So basically we look at two different groups. We look at compounds that are generally soluble and those that are generally insoluble, and then, of course, there have to be some exceptions. So generally soluble compounds, any ionic compound that contains a group 1A cation. Lithium, sodium, potassium, rubidium, cesium, group 1. You don't need to memorize the individual ones because they're all in group 1. You just remember group 1 cation. So if you see sodium dichromate, sodium's in group 1, that's going to be soluble. There are no exceptions to that one. Also, if it starts with ammonium, if it has ammonium ion in it, it's soluble, no matter what the other ion is. And then these anions, any compounds containing these anions are going to be soluble. Nitrate, acetate, chlorate, and perchlorate. No exceptions. Then we have the halides. Not fluorine. I think of the halogens as being sisters. They're nonmetals, so they're feminine in my Mrs. K's chemistry land. Fluorine, chlorine, bromine, and iodine. Fluorine is the little sister. So we'll often see that chlorine, bromine, and iodine do things very similarly, but fluorine is a little odd because she's the little sister, and kind of like the little brother of the element family, kind of gets away with doing things differently. So chloride, bromide, and iodide. If this is the anion in the compound, it's usually going to be soluble, except if we have these with silver, with mercury 1, or with lead, lead 2. So lead 2 chloride, not soluble. That would form a precipitate. Lead 2 iodide forms a precipitate. That's that yellow precipitate we saw just recently. And then sulfate compounds are generally soluble, except here we've got silver and lead 2 again, and then these are some of the group 2A metals, calcium, strontium, and barium. Barium sulfate forms a precipitate. It just does not dissolve in water. And then we have the ones that are generally insoluble. Compounds containing carbonate, phosphate, chromate, or oxalate are generally not soluble. The exception here is group 1A compounds and ammonium. The way I use the solubility rules is I start at the top. And so let's say we were doing, let's say we were pushing the wrong buttons. Let's say we're trying to decide if lithium carbonate would dissolve in water or not. I would start at the top here, group 1A and ammonium. Oh, lithium is group 1A. Those are soluble, no exceptions. I don't need to go any farther. I don't need to go all the way down here and see that carbonate compounds are generally insoluble except when they're paired with group 1A metals. Because the group 1A metals, their compounds are always soluble. So that one is soluble, and so if we need to indicate the phase, we would say it's aqueous because it'll dissolve in the water. What if we had calcium carbonate? Well, we go through the list. I'm not finding calcium or carbonate among these things that are generally soluble. Here's carbonate, generally insoluble. Not one of those exceptions, so this is not going to dissolve in water. That's one of the substances that forms the white hard water deposits on your faucet in the bathroom. And then we see that oxides and sulfides are also generally insoluble. Again, group 1A and ammonium are exceptions. And then calcium, strontium, barium. So you see calcium, strontium, and barium are going to show up as exceptions to several different things. And then we've got the hydroxide ions. Hydroxide compounds are generally insoluble except for group 1A and ammonium. And then with calcium, strontium, and barium, they're considered slightly soluble. So these are things that you're going to need to know in Chem 1A. So you might as well memorize it now. You'll forget it again before you get to it in 1A, but then when you need to memorize it again, it'll be a lot easier. Can you pass this class without memorizing this table? Sure, you can. But at the very, very minimum, you need to be able to look at a table like this and use it correctly, okay? So let's practice a little bit. Classify each of the following compounds as soluble or insoluble in water. So I'm picturing those rules, the table in my mind. And here we have silver ion and nitrate ion. The first in the soluble ones was group 1A and ammonium. I don't have one of those. Next was nitrate, right? In that second line, nitrate compounds are always soluble, no exceptions. So silver nitrate will be soluble in water. It will dissolve. Calcium sulfate. It's not group 1A or ammonium. It's not nitrate, perchlorate, chlorate, or acetate. So in that next group, sulfate. Sulfate compounds are generally soluble except, I skipped the halides, except calcium. So calcium, strontium, barium, along with silver and lead. So calcium sulfate is insoluble. How about potassium carbonate? Soluble. Potassium is group 1A metal, soluble. Now, having been around the block a couple times in life, I have recognized that you can't always do things perfectly and you can't always do everything to your very best, right? Because there's too many things. You just can't do it all. So sometimes you have to say, well, there's no way I can learn all of this stuff in this class. But sometimes just learning some of it will be enough to get you through. So in this table, I would say one of the really important things is these first two. If you can remember those, that'll get you through a lot of questions where you would need these solubility rules. Group 1A and ammonium, nitrate, acetate, chlorate, and perchlorate. If it's got one of those ions in it, it's soluble. No exceptions. That's a pretty short, easy list to memorize. So I would say at the minimum, memorize that, okay? Any questions? So when we have a precipitation reaction, we've got these two ionic solutions and we're mixing them together. And I showed you how we swap partners. And then we can look at these and predict if a precipitate is going to form or not, because we look at the possible products and we use the solubility rules to determine whether they're soluble or not. So here, lead-2 iodide. Iodide compounds are generally soluble except for lead-2. So this one's a solid, there's our precipitate. Sodium nitrate. Sodium compounds are always soluble. Nitrate compounds are always soluble. That one's going to be soluble. This is what we call a molecular equation. We're representing each of these things as a formula unit or a molecule. So these are all ionic compounds, so they're all being represented as their formula units, their regular chemical formula for the compound. But this is a soluble ionic compound. When it's dissolved in water, what does it do? dissociates. It separates into lead-2 ions and nitrate ions. So this doesn't really reflect what's present in the solution. Sodium iodide is a soluble ionic compound. It dissociates into sodium ions and iodide ions. Lead iodide is insoluble. It does not dissociate. These ions stay together. They like each other a lot. And then sodium and nitrate, this dissociates. So molecular equations are useful, but they don't really describe what's really going on in solutions. We've learned enough chemistry now that we can predict products of equations like this. Reactions like this are called double replacement reactions. Because as I showed you when we looked at this as a precipitation reaction, what's happening in here is that lead and nitrate are coming to the mixture together, sodium and iodide are coming in together, and then they're swapping partners, right? They're switching it up. That's double replacement. Two people are getting replaced. So these are steps for predicting products of double replacement reactions. And we'll do an example, and I'll do all of this. Write the formulas for the ions below the reactants. The formulas for the ions with their charges so that you can see what you're dealing with. Then switch the anions. It's like, lead-2 came in with nitrate. Well, let's see how lead-2 gets along with iodide. Switch the partners and write those next to each other. Then write formulas for those products. You have everything you need. You've got the individual ion formulas with their charges. All you have to do is look at the charges and see how to put them together. We learned how to do that. Check the solubility of each product. Yes?
Do the reactants stay with the reactants and the products? Will the products stay on that side?
The reactants will stay on the reaction side of the arrow. And what we're going to do is we're going to see how they're going to rearrange themselves to make the products. If all of the products are soluble, then there's no reaction. So if the two pairs of ions go to the party and they mingle around and nobody hits it off, there's no reaction that occurs. All that happened is they mixed. Mixing is not a chemical reaction. The formation of a solid and a new substance that's insoluble is a reaction. So then you write the phase for each product, aqueous if it's soluble, S if it's insoluble, and you balance the equation. So let's do an example, or two examples. Write balanced chemical equations for each of the following double replacement reactions. So aqueous zinc sulfate is added to a sodium carbonate solution. Well, let's stick the arrow in here so we can separate reactants from products. Sometimes you're given words like this, sometimes you're given the formulas. We need the formula for zinc sulfate. To write the formula, we need the ions first. So zinc, what's the charge on zinc ion? 2 plus. There's no Roman numeral there because it's groups 1A, 2A, 3A, zinc and silver. So we're counting down aluminum's plus 3, zinc's plus 2, silver's plus 1. So we've got zinc ion. What's the formula for sulfate ion? SO4, it has a negative charge, 2 minus. And then sodium and carbonate. Sodium is Na, it's in group 1A, and so it's got a plus 1 charge. Carbonate, CO3, 2 minus. To write the formulas for the reactants, I'm going to look at the charges. So I want to put zinc and sulfate together. I have plus 2 and minus 2. I don't need any subscripts or parentheses or anything. I just put them together. So that's zinc sulfate, and I'm told that this is aqueous. And then I need to put sodium and carbonate together. The charges have to add up to 0. So I need 2 sodium ions and 1 carbonate ion. So this is going to be Na2CO3, and it says it's a solution, so aqueous. So that's from chapter 2. Now what we're going to do is we're going to swap partners here. This is a very conventional party. And so we've got guys interested in girls and girls interested in guys. Okay, that's not saying any value judgments on people's relationships. Okay, it's just that opposites attract when it comes to electrical charges. You can't put a zinc ion and a sodium ion together. They will repel each other because they have positive charges. So it always has to be positive negative. So we're going to try zinc with the other anion, carbonate. And we're going to try sulfate and sodium together. See what happens. So I'm going to write, so here I've written the formulas for the ions below the reactants, and now I'm going to swap the partners and write them down here. So it doesn't matter if you put zinc first or sodium first. But in a formula, it's always the guy first and then the girl. It's Mr. and Mrs. John Smith on the wedding invitation. Because we all decided to do it that way. No other reason. The positive ion is always first and the negative ion is second. So let's do zinc 2+, and we're going to see how he gets along with carbonate ion. And then we're going to try sodium ion with sulfate ion. Okay, so how would we put these two together to form an ionic compound? We look at the charges. +2, -2, if we just shove them together, they'll make a nice neutral compound. So we've got zinc carbonate. We're going to need a state symbol in there, so I'm going to leave some space there. And then we've got sodium and sulfate. Sulfate has a -2 charge. It takes 2 sodiums to balance the charge. So Na2, SO4, and again, we need a state symbol in it. Any questions? Now we use the solubility rules. So zinc and carbonate. I'm mentally going through the list. I'm a visual person, so I have like this picture in my mind. So I'm going through the list, and I'm not finding zinc or carbonate in the top table of the usually soluble. I get to the insoluble ones, and carbonate is there. The exceptions for carbonate are the group 1A metals and ammonium. Zinc isn't one of those. So zinc carbonate is a solid. It is not soluble. What about sodium sulfate? Soluble. Sodium anything is soluble. It's in group 1A. So this is aqueous. And then I need to balance the equation. We can see that the carbonate ions and the sulfate ions stayed intact. They didn't fall apart. And so we can balance those as units. So here I have 1 zinc ion, and here I have 1 zinc. Here I have 1 sulfate, and there I have 1 sulfate. Here I have 2 sodiums, and over here I have 2 sodiums, 1 carbonate, and 1 carbonate. Cool beans. I don't need any coefficients. It's balanced by itself. Any questions? You should always check, though. Let's do the second one here. Aqueous manganese 2 nitrate is added to a potassium hydroxide solution. So here's our reaction arrow. Manganese 2. Well, that's Mn. 2 plus. It's a +2 charge because that's what the Roman numeral tells me. Nitrate, NO3 minus, because I memorized it. Potassium hydroxide. Potassium is K, it's in group 1A. It has a +1 charge. Hydroxide is OH minus because I memorized it. Then we look at the charges and we put them together. So manganese needs 2 nitrates, NO3, 2. We could look this up in solubility rules, but we don't need to because we're told that it's aqueous. Potassium and hydroxide, +1, -1. They just need 1 of each, so that's KOH. That's also aqueous because we're told it is. Now we're going to swap partners and see what happens. So manganese 2 plus with hydroxide OH minus and potassium with nitrate. So I look at the charges. Manganese has a +2 charge, hydroxide has a -1. I need 2 of the hydroxides so that the charges of these are going to add up to 0. Potassium and nitrate, I just need 1 of each because their charges are the same. And there are my products. Okay, now we have to check solubility. Manganese hydroxide. We go through the list. Hydroxides are generally insoluble except for group 1A, ammonium. And then calcium, strontium, and barium are slightly soluble. Manganese is not one of the exceptions. So manganese 2 hydroxide is insoluble. It is a solid. That's our precipitate. KNO3, soluble. Potassium compounds, nitrate compounds, always soluble. And then we need to balance it. I have 1 manganese and 1 manganese. I have 2 nitrate ions, and over here I only have 1 nitrate ion. So I need a 2 in front of that. Here I have 1 potassium, and over here now I've got 2 potassiums. So I need to put a 2 over here. And then I have 2 OHs, and over here I have 2 OHs. And so there's our balanced chemical equation. Any questions? So the molecular equations don't describe how the strong electrolytes dissociate into ions. And so we have another type of equation that does. It's called an ionic equation. Instead of showing molecules or formula units, it shows the ions. So it represents compounds that exist primarily as ions in solution as the ions in solution. So here is our example molecular equation. If we want to write an ionic equation, we're going to look at anything that's aqueous and separate it into ions. The only exceptions would be weak bases or weak acids, because those are weak electrolytes. And so they're present primarily as molecules and not as ions. But ionic compounds that say aqueous are going to be separated into their ions. So here I have lead 2 nitrate, and it says it's aqueous. So I'm going to write that as the ions. So it's lead 2 plus, and that's going to be aqueous. And then it's nitrate ion, also aqueous. But how many nitrate ions are there? There's 2. When 1 unit comes apart, I get 1 lead ion and 2 nitrate ions. And here we have another soluble ionic compound. I have 2 formula units of sodium iodide. Each one is going to give me a sodium ion and an iodide ion. And I've got 2. So I'm going to get 2 sodium ions and 2 iodide ions. In the molecular equation, there are no charges shown. In the ionic equation, we do show the charges because we're showing the ions separated from each other. Lead 2 iodide. What is this doing in this solution? Is it ions separated, mixing about? No. It's insoluble. It's a solid. It's sitting at the bottom of the beaker together. Lead and iodide are together on the back porch. So if it's a solid, you just copy it down as is, because that's describing what it's actually doing in solution. And then here we have another aqueous one. So this would make 2 sodium ions and 2 nitrate ions. Pour planning. Any questions? These ionic equations get really long. If you run out of space on your paper, here I just kind of bent it around because it was just a tiny bit. But if you run out of space, just kind of indent and continue on the next line. That's what we usually do. And then we have net ionic equations. What's the difference between your gross pay and your net pay on your paycheck? Taxes, right? So, maybe you get, I don't know, $1,000 on your paycheck, but do you get to take home all of it? No. The net paycheck is after they've taken out for FICA and Medicare and all those other things in your federal and state taxes. And so you maybe get to take home $800 or something. The net ionic equation is just the ions that are actually doing something. So here is the the ionic equation that we just came up with. Is anything happening to the lead ion? Here it was aqueous, and over here now, yeah, it got involved with iodide, right? Something happened to lead. What about the nitrate ion? Here we've got 2 nitrate ions, and over here we still have just 2 nitrate ions. They're just floating around at the party, mingling, having a nice time, but nothing earth-shattering has happened. Those are called spectator ions, because nothing really happens to them. You go to a boxing match, do you come home with black eyes and a bloody nose? Not unless things got really out of hand, right? The spectators sit and watch 2 people beat each other up. I've never understood why that's so fun, but it's a guy thing, I think. They're spectators. They're just watching the action, not actually doing anything. Do we really need to have them written down in the equation? Not really. They didn't do anything. In this reaction, if we had acetate ion here instead of nitrate ion, would lead and iodide still hook up? Yeah. The people watching have no influence on that. And so what we do for a net ionic equation is we identify the spectators and we just cross them off. We say, well, nothing happened with nitrate. There's 2 NO3 minuses over there and there's 2 over here. Same on each side. It's like crossing out variables in an algebra equation. What's the other spectator? Sodium. Here's sodium ion, sodium ion. Didn't participate in the chemical reaction. It was there, but it was just watching. So we cross the spectators off, and then we just write down what's left. So what was really happening here is that lead 2 ion and 2 iodide ions combined to form lead 2 iodide, which is a solid. This is the core the net ionic equation, the important part. The important part of your paycheck is the stuff you actually get to take home, right? Any questions? Example. Consider this reaction occurring in aqueous solution. Write a complete ionic equation and a net ionic equation. A lot of books will call the ionic equation either a total ionic or a complete ionic equation, just to kind of point out, yeah, we want all the ions. And the net ionic is where you get rid of the spectators. So here we have a balanced molecular equation. We need to write the ionic equation by separating strong electrolytes into ions. So first off, here's something that's aqueous, but this is an acid, right? We have to ask ourselves, is it a strong acid? Yes, it is. You can go look at the list of 7 strong acids. HBr, HI, and HCl are on that list. HF isn't because she's the little sister, right? She's not really big enough to be a strong acid. So this is a strong acid. Strong acids ionize completely, and so we write them as ions. So that's going to give us 2 H plus ions and 2 bromide ions. Oh, I forgot the 2. I said it, but I didn't write it. 2 Br minus. Because in this balanced chemical equation, I have 2 HBr molecules. When 2 molecules ionize, I'm going to get 2 hydrogen ions and 2 bromide ions, 1 from each molecule. Excuse me. Calcium hydroxide, is this a soluble ionic compound? The AQ tells us it is. So we're going to separate this into ions because soluble ionic compounds are always strong electrolytes. So I'm going to get calcium ion and 2 hydroxide ions. Because in this one unit, there's 1 calcium ion and there's 2 hydroxide ions. If you pay attention to the formulas and write these down, then it'll be balanced all by itself. Otherwise, you have to go back and balance it. Is water a strong electrolyte? No. It's not an ionic compound. It's not an acid. It's not a base. It's not an electrolyte. And the other clue to that is the state symbol here, liquid. If it says solid, liquid, or gas, do not separate it, just copy it down. So for the water, we'll just say 2H2O, liquid. And then we have another soluble ionic compound, and so we have to separate that into its ions. Any questions? This is the ionic equation. And if you go through and check, you'll see that it is balanced. It also wants a net ionic equation. We need to identify the spectators. What ions are the same on each side? Bromide. Here we have 2 Br minus, and over here we have 2 Br minus. Those are spectators. Just hanging around, watching the action, not actually participating. What else? Calcium. Here we have calcium plus, and we started out with calcium plus. Nothing really happened with calcium. So the net ionic equation, we're just going to write down what's left. Well, what's left? We've got 2H plus, aqueous, and 2OH minus, aqueous. Those are the reactants. And on the right side, we have 2H2O, liquid. Now, what's a little funny about that equation? Is it balanced? Well, we've got 2 hydrogens and 2 hydrogens, a total of 4 hydrogens on the left and 4 hydrogens on the right. 2 oxygens on the right, 2 oxygens on the left. It's balanced, but we'd really like the lowest ratio. Instead of 2 to 2 to 2, we'd rather have 1 to 1 to 1. And so if you're entering that in online homework, it's probably going to tell you it's wrong. H plus OH minus gives H2O. Any questions? Yeah.
How come when you're writing the equation, you wrote the 2 hydrogen and 2 bromine, but on the other side, if you split it out even farther, but with the other side with the H2O, it stayed the same?
Okay, that's a good question. Why did I separate these guys and not separate the H2O? Because we only separate into ions things that are strong electrolytes. Strong electrolytes form ions, whether by ionization or dissociation. Water is not a strong electrolyte, and so it's...
Same with the other one too?
Which one?
The
Hydroxide? Hydroxide is a polyatomic ion. And so here we have an ionic compound. Ionic compounds, at least as far as we go in general chemistry, always only have 2 kinds of ions. And so this isn't calcium and oxide and hydrogen ion. It's hydroxide ion. It's a polyatomic ion. Any other questions? Let's do another example. Write the molecular, ionic, and net ionic equations for the reaction that occurs when aqueous solutions of lead acetate and calcium chloride are combined. Well, what do we have here? We're talking about combining aqueous solutions, right? Here we've got lead acetate and we have calcium chloride. We need to start with the reactants. We're given the names, not the formulas. In the last one, I gave you a balanced molecular equation and said, let's just take this apart. Here, I'm just giving you the names of the reactants, and we have to write their formulas and actually predict the products. So the first thing we're going to do is we're going to take lead acetate. This is straight out of the book, and they did that. Does lead need a Roman numeral? It does. I will give it a Roman numeral. We're going to give it 2. Lead 2 acetate. We need to know which lead ion it is. So lead 2, that's Pb 2+. Acetate. That's one you're supposed to memorize. C2H3O2 with a -1 charge. C2H3O2 minus. Because we said so. No other reason at this point, just because. That's acetate. So we could put these together to form a compound, lead 2 acetate. And we do that by looking at the charges. We've got +2 and -1. You can do the crisscross thing, you can think about it however you want, but we should all come up with the same result. Pb, C2H3O2, 2. This is a polyatomic ion, a bundle pack, a bunch of things bundled together at Costco, and we want 2 of the bundles. So we've got the shrink wrap around our bundle pack, and on the outside we have how many of them? Pb, C2H3O2, 2. And we know that that's aqueous because they told us. But we could look it up and we would find that it is aqueous. It is soluble. Calcium chloride. Well, calcium is Ca. What's the charge on calcium? 2+, because it's in group 2A. Group 2A metals form +2 ions. Chloride comes from chlorine, and we look at the periodic table. It's in group 7A. 7 minus 8 is -1. Chlorine has a -1 charge. Then we look again, we've got the +2 and the -1. We need 2 chlorides to balance the charge on the calcium. So this formula is CaCl2. And this is also aqueous. I don't use parentheses here because this is a monatomic ion. So I'm not going to put parentheses in unless I have to. Any questions? Mm-hmm.
You know that's aqueous?
Because it says aqueous solutions. But we could also look it up in the solubility rules, and we'd see that chloride compounds are soluble and that calcium is not one of the exceptions. Silver, lead 2, and mercury 1 are the exceptions. Now we need to figure out what the products are. We're going to swap partners. So we've got lead 2. He came with acetate. We're going to see if he'd like to leave with the other one. Chloride. You can also think of this as putting the outside 2 together and the inside 2. We're just switching partners. I used to call this wife swapping, but analogies change over time. And so then the other combination is the calcium ion with the acetate. So we're going to put Pb 2 plus with Cl minus. We're going to get PbCl2. We need a state symbol in there, a phase. And then we're going to put these two together, and we're going to get Ca, C2H3O2, 2, and need room for a state symbol. Any questions? Mm-hmm. Like what? Sometimes you're always going to do this swapping thing and putting them together. All of the examples we've seen so far, one of these has been an insoluble compound, and the other's been soluble. You could have both of them be soluble or both insoluble. But those are the possibilities. You guys.
So the ionic equation and the net ionic equation always have the charges. The molecular
Right.
is the one that doesn't.
Molecular doesn't have the charges. The ionic do have charges because ions have charges.
And then the net ionic just wants which ones were active in the.
Mm-hmm. Yeah. Okay, so we need to identify this lead 2 chloride. Is it soluble or not? And go down the list. It's insoluble because chloride compounds are generally soluble except with lead 2. So that's solid. And then calcium acetate. Well, the second line of that chart says that acetate compounds are always soluble. So that's going to be aqueous. And we need to balance it. Is it balanced already? Yeah, it happens to be. Okay, so there's our molecular equation. And then we want the ionic equation. So we're going to take everything that is a strong electrolyte and separate it into ions. This is a strong electrolyte. It's a soluble ionic compound. This is a soluble ionic compound. The one at the end is a soluble ionic compound. Lead 2 chloride is insoluble. It precipitates, it forms a layer at the bottom. It is not dissolved into ions. So we're not going to separate this one, but we're going to separate the others. Here, we have all the notes that we need right here. We already figured out all the ion formulas with their charges. So this one, if I take this apart, I'm going to get 1 lead ion, and I'm going to get 2 acetate ions, because there's 2 of them in here. So I've got Pb 2 plus aqueous plus 2 acetate ions. And then here, in CaCl2, I have 1 calcium ion, I have 2 chloride ions. So there's a subscript there. Calcium ion and 2 chloride ions. This is insoluble. It's not a strong electrolyte. And so we're just going to copy it down. If the symbol is S, L, or G, solid, liquid, or gas, don't separate it into ions. And then the last one is a strong electrolyte, so we've got calcium 2 plus and 2 acetate ions. That's our ionic equation. If we copy things down carefully, it will already be balanced. For the net ionic equation, we're just going to cross out the things that didn't change, the spectators. So we see that acetate is present here as an aqueous ion, and it's present over here as an aqueous ion. And calcium is present as an aqueous ion on both sides. Is lead-2 ion present in the product? It is, but it's not aqueous anymore. It's not floating around. It's stuck to the iodide, and it won't dissolve anymore. It's not that the lead-2 disappeared or it isn't there, but it's been changed. Lead's in a relationship right now. He has to think about iodide's feelings when he does stuff, right? It changes you. So these are the spectators. So I'm not going to write those down. And we're just going to write down Pb2 plus came in a free man. And chloride came in a free woman. And they hooked up. We have PbCl2. Maybe they're happy about it, maybe they aren't. I don't know. They're ions. They can't talk. They don't have feelings either. Any question?